This is the first lecture for Chapter 10 for Stats 253, and this is a chapter on linear regression. Linear regression begins with a scatter plot, which is just a plot of the data points as though they're dots scattered on a graph. And for all the formulas here, we'll have them on just two axes. So the horizontal axis we'll call X, and the y-axis, the vertical axis, is called Y. That is your response, or your dependent variable. X is independent variable. You can remember that from algebra. And this is the dependent variable. Okay, they'll have real names in the data that you collect, but we're going to just use X and Y. And you can see the tutorial in R on how to do scatter plots, and also on using R for linear regression. Now the goal here is to represent all these scattered data plots with some sort of curve or a line that fits the data. If you can get a straight line through the data, and there's criteria for how to do this, but if you do have a straight line fit and there are only two variables, an independent variable, one X and one Y, this line is called simple linear regression. This process is called multiple linear regression if there are more than two variables. For example, if for simple linear regression, you might be looking at height for the Y variable and age as the X variable. If you for multiple linear regression, you might look at something with time, temperature, pressure, several variables, all to determine one other answer. For example, fish count, depending on atmospheric pressure, temperature, water temperature, year, all kinds of things might go into this, and so you'd have more than one variable. I just made that up, so anybody in Fish and Game, you know how to do that. But we're only going to study simple linear regression. In some cases, the data values will form a more complicated curve. It can be some sort of polynomial curve, might look sort of parabolic. It could also be cyclic. Again, in Fish and Game, you study the populations. A famous one, or classical one to study in math, are rabbit populations versus lynx, and those are cyclic, and those are usually represented by some sort of a sine curve. Here's just an example of a scatter plot and a linear fit through that scatter plot. You can see even if you didn't have the line in here, you could tell a downward slope. You could see that many of the data points seem to be sort of convergent and to be close to each other. You could see that a linear plot would fit this. It's important to look at these, and I'll show an example of how you can't just depend on the math to determine if there is a good linear fit. You have to look at the scatter plot and look at the data. You can make a few remarks on what you are going to do with that line. One thing you can do with a line is you can use it to predict a value that you didn't measure. For example, in this case, it looks like a weight of 3,000 pounds was not a data point. But if you use the line, you could estimate where whatever this 10, 20, 30, 40 is with respect to weight. You could try to find a value for the response variable at points you didn't measure that lie between the points you measure. This is called interpolation. That can usually be done. That's not an issue for a good fit. Extrapolation. Extrapolation means a prediction beyond, sort of outside of the domain of your x-axis, trying to predict a value out here. That's not always so good, and that has to be done with great care. But that's something you can do with a line. Another thing you can do with a line is, instead of taking all these data points and feeding them into another program, you can take the equation for the line and put it into another program. That's a lot better and works a lot, works well. For example, if instead of being weight here, we had see, let's say this is cost for some items we're selling, and here's the number sold. Right. Well, first of all, you don't want to deal with this noise in the data. This point's probably an outlier, but you don't know for sure. But all these are a little bit off. You don't need to deal with all that noise. You just need to know the trend. Okay, once you have this line though, you could take this line and feed it into another computer program or some other analysis that might give you profit. Now you've got cost, number sold, you really are looking for profit. Or maybe this line helps you make some personnel decisions. You might not need too many salesmen if you're not selling too many things. On the other hand, maybe you need a lot of salesmen, I don't know. But you might need more workers to make a more expensive car. Or whatever it is that you're making. I guess $5,000 is a pretty cheap car. All this comes under the heading of modeling, which is a big part of both mathematics and all kinds of sciences as well as statistics. Now once you've looked at the data and decided it looks like it could be represented by a line, you would like a mathematical sort of verification of this correlation. And what is used for that is a correlation coefficient. There's several of them, but this one is called the Pearson product moment correlation coefficient. It has a very nice long name, but it has one abbreviation, and that's the lower case letter R. So R generally means correlation coefficient anyway, not necessarily linear. Okay. Now this is a concept that's listed here, applies for all correlation. Correlation coefficients range, they have values that range between -1 up to 1. And you think -1 means they're not correlated. No, it doesn't. It means they're inversely correlated. In this case, we're talking about a linear relationship, so we'll talk about it linearly, but it applies to other correlations. Basically what this means is that as the dependent variable increases, as the independent variable increases, as x increases, y decreases. Here's x, and it's increasing in value. Here's a y. Your data points might start up here and go down. Right? If these lie very close to a line, or they lie on a straight line and it's descending, the correlation is -1. +1 is the same, except that as the x values increase, the y values also increase. So if your x, here's your y, let your x values increase. Your data might start here, and as x gets bigger, so does y. That's a direct correlation, and R has a value of 1. So at the extremes of -1 and +1, the data is very linearly correlated. The sign of this correlation coefficient tells whether it's a direct correlation or an inverse correlation. Okay, what about R equals 0? If R equals 0, there is no linear correlation. We've seen this before in probability when events were independent. We called them independent. Drawing a queen from a deck of cards and rolling 7 on the dice, those are independent of each other. There is no correlation between them, if we want to say it in these terminology. So if R equals 0, there is no linear correlation. We're looking only at linear for this correlation coefficient. There may be another kind of correlation, but for our cases, there would be no linear correlation. Now here's some examples of some scatter plots. Here, instead of dots, it's the data is represented by the asterisk. Okay, figure 1. The data plots pretty much fall right on a straight line, and as the x increases, y also increases. So I draw a straight line through it. Not quite. All the data points aren't quite lined up. This would have a correlation coefficient of really close to 1. Maybe it's going to be 0.95. It'll be positive because they're increasing. You see how the slope is increasing? Because it's a direct relationship. Here is the same thing, except it's going down. In fact, I think all these data points really line up. The correlation coefficient here is probably exactly -1. how about figure 3? In figure 3, there is no linear relationship between the data points. This has a linear correlation coefficient of 0. I don't know if there's any other correlation between these either. Seems like there's no correlation. Okay, now how about 4? 4 is more a case that you would get in real practice. The data points aren't all lined up. They're sort of clumped up though, and they appear to be clumped up along sort of in a linear fashion. And the relationship seems to be direct. As the x values increase, the y values are also increasing. So we can guess a correlation coefficient is going to be close to 1. It will not be exactly 1. Look at all these points that are off. Okay, and it's going to be positive, maybe 0.85. Just for completeness, I'll try to sketch out here some data values that are not have a different correlation. Okay, so here's x and here's y, and let's just put our data points here like this. And we see some kind of trend like that. Okay, are these linearly correlated? Well, if you run a straight line through it, you might get some of them, but you won't get them all. It certainly won't be a good fit. But perhaps you could draw a parabola through this. That's a pretty good fit. So instead of being linear fit, this is a quadratic fit. Here would be an example of something that's more cyclic. So you have a population, and it goes up, down. You don't have all this data, and you've got a bunch of data here. Okay, that's cyclic, right? You wouldn't fit that with a straight line. That'd be pretty much useless, but you could fit it with some sort of a sine wave. And of course, some data has no correlation at all. Okay, now there's a way to calculate this Pearson product moment correlation coefficient, which I would just refer to as the correlation coefficient. And this is sort of the introduction to the notation for linear regression. There are really only a few terms in it, and once you get those straight, everything follows from it. The last lecture the last file in the written lectures for chapter 10 is a summary of the formulas, and that starts with the notation, and I'm going to move to that file right now. So this is from the file of the summary of the formulas, and at the start we're just going to have a notation. X is the independent variable, Y is a dependent variable. Now each data point is going to be represented by the ordered pair xi, yi, where I is the counter ranging from 1 to n. I didn't put that on there. So here's the data point, just like you've done so far. X bar is the mean of the x data values. We're not used to taking the mean of the x data points. We use data values. We usually don't worry about the mean of the x's. We're very used to taking the mean of the response variable of the y. Same thing, add them all up and divide by n. But this is used, both of these are used in the calculations. So the bar means mean values of the x values, mean of the y values. Now I want to mention one other notation that we won't use right away, but we'll use it in the second lecture, and that is the hat. Okay, so y hat, the hat refers to the value of y on the line that you use to fit through the data. This would be a calculated value. So the hat on it means a calculated value. Okay, and of course there's an ordered pair because it's on the graph. If you say you have a data point xi, you put it in your formula and you and you find the value of the line at that data value, that will be yi hat. Okay, so the I is the data value. This was one of your data points, or the x is the data point. This was a calculation. Now we'll go back to the other lecture. Now we're looking at the formula for the linear correlation coefficient R, and it looks complicated at first. When you look at it and break it into pieces, it's very easy. Mendenhall writes it this way. He uses another notation, and this is common in statistics, so let's look at what this notation means. Well, it doesn't mean what it says, but all right. The the first S stands for the sum, and it's supposed to be sum of the squares. Okay, but then there's two subscripts. Let's look down here in the denominator, and we see two x's. That refers to this term. I'm going to write this out. Well, you can see it from here. Here's the sum, and here's the square. Okay, fine. The two x's, if you expand this, you would have xi minus x bar times xi minus x bar. That's squaring something. You see one x term and another x term. It's same for the two s's and the double y. You've got a sum, and you squared the y's, and if you wrote it out, you would have yi minus y bar, yi minus y bar. Okay? Now look in the numerator. It's a little different. I'm going to erase the screen here. Okay. That's what we're working with. So we have SSXY, and that is defined to, it's an abbreviation for I equals 1 to n of xi minus x bar, yi minus y bar. Okay, sum. All right, I'll agree with that. Square, that's not a square, that's just multiplication, but we still use the notation. So the s here, although it is read square, really means multiply together two terms. In this case, they're both x's, so it will be a square. Both y's, it will be a square. X and a y, it's not a square, but just multiply them together anyway. So here's your x term, and here's your y term. So now maybe you understand that notation a little better. Let's look at the formula, though, and see how little is in it. There's only two terms in it, actually. You have a data point, well, all of your data points, minus the x values minus their mean. And then you have another y minus its mean. That's all. In this case, you take the x's, square them, and add them up. Here you take the y's, and you square them and add them up. And here you just multiply those two together and then add them up. So at first it looks complicated, but it really isn't. Let's look at an example. I like doing things in these tables because I think it organizes it. Obviously, you'll only want to do this by hand for a very small data set. So this is the data set in chapter 10 of the text, Mendenhall text. So what we have here are the x values. So add them all up, divide by 5, and you find the average. Okay. Here are all the y values. Add them all up, divide by 5, and you find that average, the y bar. In the next column, I took the x data value minus the mean. For example, here, okay, so I take 1 minus the 3, and I got a -2. Well, there's an equal sign there, and here's my -2 right here. So I do that for all the data values. This is data right here, and here are the means up here. Okay, now I take each one of these and square them. So -2 becomes 4, -1 becomes 1, etc. Add them all up, and that's going to give me one of the terms that's used in the correlation coefficient. Now I'm going to do the same thing with the y's. So I'm looking at the y value here minus the mean for y, and I get these values. Then I move over to this column. I square every one of those values and I add them up and I get a 6. I'm going to use that. And then for the numerator, it you take this, the values in this column, and you multiply it by the values in this column. So in this case you've got -2 times -1, and I got a +2, -1 times -1, I get a 1, 0 times 0, etc. Then you add all those up and you get a 7. Like I said, you only want to do this for a very small data set. Okay, so here is our correlation coefficient. Here was the x's, and this is the x term, came off of here. Here's the y's. This would be SS double y right here. And now the numerator is right here. And when I multiply all this out, taking the square roots, etc., I get an answer of 0.9037. That's a correlation coefficient of approximately 1. That says that this data is highly linearly correlated, and it's correlated in a direct fashion, meaning that as the x values increase, the y values also increase. Now, you might want to say, why bother with the scatter plot? Let's just throw all the data into the computer, find the R, and we're good to go. Let's fit it. Also need to make another remark. In the text, Mendenhall starts by fitting the graph, fitting the line to the data. Then he calculates the correlation coefficient. I think it's makes more sense to do it the other way. Look at the scatter plot. Find the correlation coefficient. If it's not close to 1, why bother fitting the line? Okay, so that's why I'm doing it in this direction, with the correlation coefficient first. But I want to show you here a classic result that someone has been put together in the past, and it shows 4 data sets that have the same correlation coefficient, and this correlation coefficient is 0.816, which is pretty close to 1. This is a good linear correlation. But look at the data points. Okay, for the first one, straight line fit looks pretty good. They are off. There's some points that are off, but this is okay. Okay, I believe it here. That makes sense. This is what you would expect from a correlation coefficient of about 0.8. It's positive, so you have that direct correlation as x values increase, y values increase, the slope of the line is positive, and the data points are fairly close to the line, although not exactly on the line. How about this one? It's not linear. Okay, the correlation coefficient said was fairly high, but that's not the whole story. What would you do with this one? Obviously, this is a parabola. It should be fit with a quadratic and not a linear expression. Let's look at the third one here. Well, this correlation coefficient of 0.8 actually underestimates the linearity of this data. What's happening here actually is this outlier, which is most likely a mistake, has pulled the line towards itself and actually decreased the correlation coefficient, because the rest of the points are directly on a straight line. If you got rid of this, your correlation coefficient here would actually be 1. And what about this? Okay. Now, if you saw a scatter plot like that, you would not even try to draw a line through it. You'd say, well, that's sort of ridiculous. I need to think about this data a little bit more and understand what's going on here. Why, for a certain value of x, I got all... In fact, you're missing a lot of values here that could probably help you. You probably don't have enough data to really understand what's going on. So the important message here is that you need the human factor to look at the scatter plot and decide if the correlation coefficient that could be produced by a computer or calculator, if that really makes sense. I'd like to make one other another point that's very important, and that is that correlation does not imply causality. I've mentioned this earlier in the semester, and it really shows up here. Just because you can make a nice straight line plot or some other kind of correlation between an x and y variable, that does not mean the x variable caused the y variable. We see this mistake happening all the time. You can crunch the numbers, you can make really nice plots, it can all look good on paper, but if the basic science is wrong, it's still wrong, no matter how much they look like they're correlated. The classic example, of course, is the use of fireworks to scare off the dragon that caused the eclipse. Thinking that a dragon is between the earth and the sun or the moon causing the eclipse, if you set off the fireworks, it will scare the dragon away, right? And then the sun or the moon will reappear. There's a perfect correlation between shooting off the fireworks and having the sun or the moon reappear, since sooner or later the eclipse is resolved on its own anyway. But shooting off the fireworks did not resolve the eclipse. Of course, that's just one example, and there's many other examples in history and all sorts of science and in I don't know, popular superstitions, as well as in our own personal lives.